Yeah, thank you very much. So first, let me thank the organizers for this invitation. It seems like a very nice idea to me of the workshop, bringing together all lambdas. It's something we should do. So I will tell you about work that came out this summer that I have done with Luca Eliasiu and Mark Mezei, and it's about the black hole interior. So here's the plan for today's talk. So first I will tell you some motivation. What do we want to study? Why do we want to study it? Then I will review some results that will be basically the main tools for what I'm going to say, which is what Tom already talked a little bit about, the duality between two-dimensional theory of gravity and matrix integral, random matrix theory. And then I will go on to describe how we calculate the volume of the interior in JT gravity. Okay, so let's start with the motivation. So we want to understand black hole interiors, and one very interesting aspect of the black hole interior is that it's kind of an example of an expanding cosmology. So what does this mean? It means if I put this black hole in ADS, so here are the boundaries. So this is a two-sided black hole now, and I anchor some Cauchy slice between some fixed boundary times. I can look for the maximal Cauchy slice, and it will, as I move up the anchoring point, the boundary time, it will grow. So it will grow in general linearly, and classically, like predicted by classical gravity, it will grow forever. So there's some space being created here as you move on up in time. And the question is, what is the microscopic origin in the CFT or in the dual theory of this creation of space? So this is what we want to understand eventually. So this question in ADS CFT, you might hope that there's a handle on it because this two-sided black hole, we know very well what state it's dual to. It's dual to a particular entangled state called the thermophile double. And then if you move up this anchoring point, it just means that you consider time evolution of this state, which is not an eigenstate of the Hamiltonian, of this both-up Hamiltonian, so it will evolve in some way. So you should look at probes of this time evolved state. But the simple probes will not produce you this type of behavior where you have this kind of long growth. So for instance, correlation functions will typically thermalize, and some thermalization time, you can have some small enhancement. So if you consider some more complicated contours, or you could look at entanglement entropy, and this is also a probe that basically thermalizes in thermalization time. Okay. On the other hand, for this wormhole geometry, perturbative corrections are very unlikely to terminate this growth. So basically, you would want to look for some quantity that is not thermalizing for times that are non-perturbative in G Newton. Okay, so one candidate that has been proposed by Susskind and others is called complexity of a state. So what is this? So consider k qubits, and suppose you have some access to some simple limited operations, and you want to transform a particular state of k qubits, which is now a product state here, into some target state. So this is your task, and you can only apply, let's say, 2 qubit gates. And the question is, how many steps are minimally required to do this? So this is a kind of very discrete problem, but in this way of explaining, quantum complexity would be the size of this minimal quantum circuit. Okay, that would be, let's say, complexity of this target state. Okay, so what I'm telling you is about qubits, and it comes with a lot of ambiguities. So I tell you here's some reference state, and then there's some gate set and some circuit architecture and so on. But one thing I want to point out is that it's also ambiguous how we measure the interior of the black hole. So using the volume is one way. So we will be interested in general scaling properties of both the size of the interior as captured by different quantities and some class of quantities that we want to look at in the CFT. So let's focus on this complexity quantity now and just discuss how the time dependence of this quantity looks like. So now I will just review some simple argument for the time dependence of this complexity. So first of all, you can think about this time evolution operator as a kind of quantum circuit. So you can break it up into small layers of small time steps, and then the Hamiltonian is like an integral of some local operators. So you can kind of think about it as these simple operators, 2-qubit gates, and there's a whole layer of them. And then you apply this, let's say, some capital N times in this discretization. So it's clear from this. Yeah, so this is what I just said. If you think about this as a layer of a single circuit, that the number of gates in the time evolution circuit grows linearly, simply because it's just the size of this N here. And it's also proportional to how many degrees of freedom you have in one layer. So we can capture that with the entropy. So this is what you roughly expect, that the size of this circuit grows with entropy times time. Okay, so this is one circuit, but not necessarily the minimal one. So assuming that it's the minimal one, you can ask what's the longest time that it can keep being the minimal one. So it cannot grow forever. Eventually there will be some shortcuts. So what kind of shortcut can you get? So this is like the worst thing that can happen is that, again, we're looking at k qubits. And the question we want to ask now is like how many states are there in total, so that this time evolution can visit. So this is a continuous space, but you can imagine introducing some tolerance and say that two states are the same if they are close enough to each other. And in this case, the number of states is roughly the volume of the Hilbert space, but now not the Hilbert space, but the space of physical states, which is projective space. So for k qubits, it will be CP2k minus 1. So when k is large, the volume of this space scales in this double exponential manner. Okay, so now we want to compare this to the number of possible circuits that we can write down with a given depth. So if you have this number of fundamental, let's say 2-qubit gates that you work with, then you just need to kind of raise this to the power of how many gates you have in the circuit. So there's a width to it, that's k, the number of qubits, and the depth is n. So it scales exponentially. So the statement then is that if you have a deep enough circuit so that you can kind of have all states formed by circuits of that depth, then you have reached maximal complexity. So complexity cannot go further because there will be a circuit that gives you a shortcut. And because of this, maximum complexity is expected to scale like the dimension of Hilbert space. Okay.
So, Gabor, just to clarify, K, if we were talking about a concrete example, like would be the number of lattice points on the in the lattice C-dual CFT. How should I think of K in an actual ADS-CFT model?
Yeah, it's roughly the entropy. Yeah, so if you have two
it's
qubits,
state dependent.
Sorry?
What do you mean the entropy? It's a state dependent quantity, this K?
No, it's the number of states. So if you have, let's say, some ADS-CFT, or yeah, okay, let's say you have some QFT and you consider some time evolution, energy is conserved. So this time evolution will explore some fixed energy subset of the Hilbert space that's finite dimensional, and it's the dimension of, like K is the log of the dimension of that space. 2 to the K would be the
analog. You're considering states where this is an extensive quantity in the volume of the QFT.
Yes. Okay, so if you start with a linear growth and you assume that there's no shortcut before this, then you will reach this in some exponential in entropy time, this exponential in entropy value. So the cartoon is the following, is that you have complexity, you consider some chaotic system where there's some sort of time evolution, and then the complexity of a state will grow for a time that is exponential in the entropy, proportional to the dimension of the Hilbert space, and then it will saturate at some maximal value. So this is an expectation for chaotic systems. There are some interesting progress towards like whether this is indeed the case or what kind of conditions you have on this, but this is the kind of intuition that we want to have in mind. And then at very late times, you could have also Poincare recurrences, but I'm not going to talk about those today. Instead, what I will tell you is that, first of all, we know that semi-classical gravity, or we expect that semi-classical gravity captures this part of the curve, and we believe that this is dual to the linear growth of the size of the wormhole. Now, what I will tell you today is whether we can see this also in gravity, this saturation. And this is what we will try to do. Okay, so first, why do we think that we have a chance of seeing anything like that? So it's some very fine grained physics. You need very nice, good resolution to see this saturation. And the reason why we think that we can make progress is precisely Tom's talk, because it seems like Euclidean gravity seems to have an unreasonably large regime of validity. So I just put here two examples that Tom reviewed in much detail. Like it knows about level recursion in the energy level spectrum of chaotic systems. It also knows about entropy of the page curve. But what I just want to stress again or remind you about is that these corrections are all coming from summing topologies. Okay. So today what I will ask is basically how do we apply these ideas to the volume of the interior? What's the effect of summing topologies? Okay, so now I will move on to describe or review JT gravity as a matrix integral. Any questions at this point? Okay. Okay, so the theory in which we will do the calculation is Jackiw-Teitelbaum gravity, which is a gravity theory in 2 dimensions. So it has gravity and also a dilaton degree of freedom, this phi. So this is the action. There's a topological term, there's an Einstein-Hilbert term coupled to the dilaton, and then there's a boundary term so that we can do holography. Okay, so one comment that this is like a pretty generic theory. It arises by dimensionally reducing many near horizon, many near extremal black holes in the near horizon region. So it kind of describes some limit of universality class of physics. Okay, and then the important thing for us is that it has black hole solutions. So what is a black hole in this theory? It's basically global ADS2. And why is it a black hole? Because we put a cutoff at large constant value of the dilaton. So how does this look like in Lorentzian? So this is a particular solution of this theory that you have in Lorentzian. You have this kind of Schwarzschild light coordinates covering this Rindler patch of ADS, and this is how a constant dilaton surface looks like. So because the boundary lives here, the holographic dual system lives here. This is a black hole because you cannot send signals between the two sides. So in Euclidean, this is just the 2D version of the cigar geometry, the usual Euclidean black hole, where the cutoff surface is now at a constant radius on this hyperbolic disk. Okay, so this was black holes in the classical theory. So how do we deal with the quantum theory? So what's special about this theory is that that path integrating the dilaton out gives you a delta function restricting to constant negative curvature metrics. So essentially, these are all just Riemann surfaces with some number of boundaries. So this essentially restricts all the off-shell geometries in the path integral to be basically pieces of the hyperbolic space or the hyperbolic disk with disk topologies. So what does this mean? So here's the hyperbolic disk. So what's the only off-shell degree of freedom? It's kind of the shape of how you cut out a piece of this space so that your boundary conditions are satisfied. Okay, so there's some now one-dimensional degree of freedom that parameterizes these wiggles, and after you have integrated out this dilaton, the action you get is a boundary action, and it's a simple action. It's the Schwarzian derivative of this function, basically. And why is this nice? Because in addition to the simplification of reducing the theory, basically one dimension, you can also just exactly do the path integral of this theory. So that's a nice result by Stanford and Witten. And once you do the integral over these wiggles with the boundary condition of this proper length of this curve being fixed, you get a rather simple formula where beta is here the temperature, so the length of this curve, and gamma is the boundary value of the dilaton. Okay. So this is how a fixed topology sector works like. So we could simply solve the whole theory and do the whole path integral for a fixed topology sector. And the nice thing here then is that you can go ahead and also some topologies. So these different topologies are weighted by the Euler character. So as you increase the genus, they get more and more suppressed. And this is how they roughly look like. So by the way, I'm describing work by Saad, Schenker, and Stanford. So here you just have the path integral over the wiggles of the disk, which I just showed on the previous slide. And then you can sum these various higher topologies by surgery, basically cutting and gluing. So the way it works is that for each genus, you cut the surface into a simple geometry, which is called a trumpet. So that's this part of the geometry. So here's a geodesic separating it from the other parts of the geometry. And here you also only need to integrate over these wiggles. And in the same way as in the case of the disk, this is a one loop exact integral that gives you a rather simple formula. Now it depends also on this parameter B, which is the size of this neck, this geodesic here. Okay, so this is this part of the path integral. On this part of the path integral, you're just counting surfaces of a given Riemann surfaces of a given genus with, in this case, one border, essentially one geodesic boundary. So you get a moduli space of surfaces here. And then the remaining thing to do is to kind of integrate over the size of this neck, and that's this B integral. So this is the structure of the answer. And this works very similarly for n boundaries, in which case you get the moduli space of Riemann surface with n borders and geodesic boundaries, genus G. Okay, so essentially the nice thing here is that these volumes are known to satisfy a recursion relation. So this was shown by Mirzakhani. And this is related to a genus expansion in matrix integrals. So this was basically noticed by Saad, Schenker, and Stanford, and basically where this leads, this correspondence is that you find that JT gravity is a matrix integral. So in the sense of this genus expansion, you have the following equality, that the partition function JT gravity is an integral over a random Hamiltonian of an actual trace e to the minus beta h. Okay, so this squiggly line is because this is true in the genus expansion and in something called a double scaling limit. So these things have an infinite spectrum. Okay, so this is something that you heard a bit about in Tom's talk and leads to many questions, whether gravity is an average. So you have seen that this is a rather big can of worms, and I'm not going to open this in my talk, just use these tools to calculate. Okay, so let me move on to the third part of the talk, which will be about now the volume of the black hole interior. So are there questions at this point? Okay. So here's again how a classical black hole solution looks like in JT gravity. So how does the classical volume work? It's very simple in this case because it's just a geodesic, because in 2D, we're in 2D. So in this case, that's just a straight line in this global ADS2 that goes between the cutoff surfaces. And if you calculate this, then it has a very simple form. After you kind of remove the divergence from the usual holographic UV divergence or IR divergence, you get this formula that gives you the kind of linear growth that I was mentioning that is true for all black holes. Okay, so this is the classical story. So how do we go generalize this in the quantum theory? So let's first talk about the quantum definition of the volume in the perturbative theory, where we don't sum over topologies. So we can define a quantum volume using the Hartlocking wave function. So the Hartlocking wave function is a state that you create by a Euclidean path integral. It depends on a length of a geodesic. So it's a path integral between a geodesic boundary with a given length and between an asymptotic boundary with a given proper length, which is half of the inverse temperature. Okay, so this is essentially the bulk wave function of the term of a double state. And in general, this would be something impossible to calculate in higher dimensions, but in JT gravity, because of the simplicity of the theory, you have these one loop exact integrals. There's an explicit formula for this. It's just some integral transform of some Bessel functions. So it's known what the gravity path integral gives for this wave function. And once you have this, you can just calculate the expectation value of the volume in quantum mechanics. So you just insert essentially the operator, you put the modulus square of the wave function, and you integrate over with the appropriate measure in which these states are orthonormal. Okay, so this is kind of the picture that you do a path integral with the volume insertion. Okay, so this is a perturbative volume, and this is something that still, you can calculate it, still grows forever in a linear way. So we want to include contribution of topologies, wormholes. So how do we do that? So first, there's the challenge with how you define the quantity. And the challenge comes from the fact that once you have include topologies, there's an infinite number of extremal geodesics going between 2 points. Okay, so what do we do then? We could take, so let me, we could take the minimal one. So that would be one prescription, but we want to talk about the Lorentzian continuation of the endpoint. So that's not great because the minimal geodesic as a function of Euclidean time, it's not an analytic function because as you change Euclidean time, it jumps around and moves. So instead, we want something that is a little bit more democratic. So our prescription is to kind of sum over all of them. Okay, so this is what we do. There's a sum over surfaces of various genus, and in the given sector, you do a kind of path integral for the volume, and you sum over all the geodesics going between 2 points. Okay, there's one problem with this. This is clearly infinite. So I just told you that in these surfaces, there's infinite number of geodesics. They even will have growing lengths because one possible class of these infinite geodesics is that things start to wind, let's say around neck of a topology, or it starts to wind around a hole in the surface. So they are longer and longer, so this quantity is divergent. Okay, but you can regularize it, as we often do as physicists when we deal with infinite quantities. So one particular thing that you can do is that you could consider summing instead of the lengths, e to the minus delta the lengths. So that's now something that is convergent. You do the sum and then you analytically continue the derivative to delta equals 0. Okay, so I just want to mention that if you sum all geodesics here, then what you have here before the derivative is just the 2-point function in this theory of an operator of dimension delta. Okay.
Can you just repeat that point again? Like, what did you mean by well-defined set? Like, what was that exactly? Because you said that there's this infinite number, but what was this well-defined set? How do you classify well-defined?
Yeah, I haven't said this here. So here, one well-defined set would be summing over all of them. Another well-defined set is what we actually do, which is to sum over non-self-intersecting geodesics. So that I explain on the next slide.
But yeah. Still, there's one minimal geodesic, even if you're on a higher genus surface, right? Like there are extremal, like yes. You said that there's an infinite number, but there's one minimal geodesic.
Yes.
Okay. Thank you.
Yeah, there could be degeneracies. So
okay, even in the minimal one. So
yeah, but it's not going to be a generic thing that there are degeneracies. But if you have your boundary points chosen in particular ways, there could be degeneracies. Yes.
Okay. But you're just basically summing over the non-intersecting extremal geodesics roughly. Yeah.
Yeah. So one reason we don't like that is that if you want to plot that as a function, it will be like kind of a piecewise continuous function as a function of Euclidean time. So that's not something that we imagine would have like a nice weak rotation. So we want instead nice and analytic, so that we can weak rotate and talk about the Lorentzian black hole.
Okay. Thank you.
Yeah, so this well-defined set of geodesics. So you could sum over all geodesics, then you would get the 2-point function of some local operator. So this is not what we do for 2 reasons, which I will tell you. But first, I tell you what we do. So what we do is we sum over geodesics that do not self-intersect. So for example, if you have this example of genus 1. You could have a geodesic that goes like this. It could go on the other side too. That's also fine. It could go over the handle here. That's also fine. We sum it up. But the one that winds around, it self-intersects here. So we don't do that. So why are we not doing that? Yeah, sorry. So here's just like another figure of, in the case of genus 2, a couple of geodesics here in red, which do not self-intersect. So first, physically, we imagine that we kind of want to think about this volume as or as something that's defined on a Lorentzian Cauchy slice. So that interpretation doesn't really work with an intersecting geodesic. So you want to kind of have this as a kind of one contribution to how a Cauchy slice could look like. So this is sort of the kind of intuition of thinking about this as a state, but it's also something that we cannot really do, including these intersecting ones presently. So we just gain a technical simplicity. So if we cut along such non-intersecting geodesics, then you can see that essentially we're just introducing another boundary. So in this case, in these 2 cases, the surface just falls into 2, while in this case, I just remove a genus here and have 2 other boundaries. And this is an important technical simplification that allows calculation. Okay. Yeah, so how does it do it? So basically, it's just the same idea that we have in the case of the disk, that we have a modulus square wave function and we insert some operator here, which in this case, this regulated expression here. And for higher genus, we just sort of replace this with the case when there's some two trumpets here, and then there's some kind of arbitrary topology surface connecting these two sides. So this kind of looks like a density matrix now. So you could ask, why haven't I just defined this density matrix? Because, and the reason is that, yeah, so this is what I just said. And the reason is that this formula is a bit misleading, because if you remember, there was a sum over all geodesics, and the way you get to this formula is that you use a relation derived by Mirzakhani to get the recursion relations, which essentially relates sum over the non-intersecting geodesics with one moduli space, with one boundary moduli space in with the moduli space of this surface. Okay, so this is the actual structure that you get here with the moduli space of these two boundary surface and no sum over the geodesics, but it's not trivial how it turns into this. You need to use recursion relation. Okay, so instead of this disk amplitude, now what you write here in the L integral is an expression like this, where there's two trumpet kind of wave functions, which are these two contributions, and they are glued by moduli spaces here. And there's integral over these two next sizes. Okay, so once you have this expression, you can just turn it into the way Sad, Schenker, and Stamford did into an expression in the matrix model dual, and you get the following type of expression. So you have kind of two integrals over energies. This is because you have separated these boundaries into two boundaries, so it's really like a two-boundary quantity that you have now. And the effect of the volume insertion is that after now you do the analytic continuation to delta equals 0, is that you have a particular kernel here, which has this kind of form. So it's a large expression, but it's rather elementary, and this is what just comes out. So what's the important feature of this kernel? It's really like all the details don't really matter. What matters at late times is how this behaves when the energy difference is small. As you see, that's what the time couples do in this expression, and it behaves as a inverse square singularity that pulls together energies. Okay, so now I will analyze this quantity a bit, or tell you like how it behaves and how it's related to other quantities. So you have this spectral density 2-point function here, and in this late time regime where the energies are closed in a random matrix integral, like independently of the potential, it has a kind of universal form. So it has a kind of factorizing piece. This is a classical piece from the gravity point of view. It comes from two disk amplitudes. It has a time-independent divergence. So this is something that, so first of all, why is it divergent? It's a kind of contact term here that sets E1 equals to E2, but here I just said that you have a singularity. So this would give you a divergence, but this is in particular the divergence that is being regulated by delta, by having a finite delta in this regularization prescription that I was telling you. So we just throw this away. It's time independent anyways. So all the divergences are time independent. It's time independent because again, when E1 equals E2, there is no time dependence here. And then the important piece for us is this non-trivial correlation here. So there's two pieces to this. There's a kind of power law piece, which comes from leading wormhole geometry, this double trumpet. And then there's a kind of sign piece that cuts off this divergence when the energies are very close. So this is called a sign kernel, and this sign part comes from doubly non-perturbative contributions. So it's non-perturbative in the matrix model. It's a particular instanton. Okay, so what happens when you plug this formula in here? You can just do the integral and you get an expression like this. So first of all, you can scale out the entropy dependence completely. Both if you scale it out from both from the time and from the volume, then you get a kind of scaling curve. Okay, so it starts with linear growth, which is just the classical growth, and then it saturates to an exponentially large value in the entropy in a particular way. So this is the way it approaches it. It's a kind of slow saturation. Okay, and just a reminder that why are we happy about this? We're happy about this because this is what we were expecting complexity to do. Okay, so let me give some comments about this behavior that we find here. So that's going to be the rest of the talk. Okay, so first comment, there's like the form of the quantity is very similar to another quantity that people have studied a lot is called the spectral form factor. So it's kind of an absolute value square of a partition function that you have analytically continued in temperature. And you think about it as a function of time. And in a random matrix theory, you average it. Okay, so in that case, you also have a kind of double integral. It's fixed by the spectral 2-point function. So it's the same data that fixes the two things. And for the spectral form factor, you just have a 1 here, while for the volume, you have this kind of kernel here that pulls the eigenvalues further together. So what is the effect here that this small change does? So this is how the spectral form factor looks like in a random matrix theory. So it has this kind of decaying contribution. It has a kind of dip, it rises and ends in a plateau. Okay, so the classical contribution, that's classical gravity without topology. It gives for the spectral form factor the decaying curve. So it decays forever, and it leads to this kind of information problem that it just gets arbitrarily small. On the other hand, for the volume, it gives something that grows forever. So it does the opposite. It's something that gives you the linear growth that never stops. On the other hand, this sine kernel piece, in the case of the spectral form factor, it gives you a curve like this that it rises and then saturates in itself. So this kind of ramp here comes from this power law, and the saturation comes from this sign in the denominator. But it does its own thing in itself. So it's an internal cancellation between non-perturbatively suppressed contributions, and the total curve is the sum of the two. On the other hand, what the sine kernel does in the volume, it gives something that doesn't really do anything at early times, and at very late, it starts to grow in the negative direction with a linear slope in precisely the way that it cancels this growth here, and you have this plateau here. Okay, so this is a kind of new cancellation where you have a cancellation between the disconnected contribution to the spectral density and the sine kernel. So that's what lies behind this, and it's a universal thing. So it's just true in random matrix theory. Okay. So my next comment is about the noise. So we go back for a step or for a moment to this interpretation of gravity being an ensemble average. So then we can ask how this quantity will look like in a single member of the ensemble. And one thing we can do is to calculate the variance of it. So what would we do then? We would square this quantity and do the average in the ensemble. So there's a geometric computation that you need to do in this case. So you kind of double the number of boundaries. So there are two black holes now, and they can be connected, as Tom was explaining. But now there's two marked points, and you want to kind of sum the geodesics going between those two marked points. And this is true for both sides. So essentially, again, when you cut along these geodesics, you introduce like you double the number of boundaries. So instead of 2 boundaries, you will have 4 boundaries. So whatever you do here will result in a formula that depends on the 4-point spectral density. Okay, so what we find with a set of subtleties that I will mention is that if you do this calculation for the variance, you find that the variance grows as square root of time when the time is much larger than exponential of the entropy. So you get a curve like this, where the orange curve is the expectation value and the variance plus variance minus variance is shown here in blue. Okay, so basically there's a part of this kind of volume plateau where the time scales like e to the s naught when the noise is much smaller than the signal. It's suppressed exponentially in the entropy, but if you wait long enough for times that are e to the 2 times the entropy, then this signal to noise ratio becomes order 1. And in particular, the weird thing is that this noise doesn't plateau. Okay, so comments about this. So this is not very good for interpreting the quantity as complexity, because for complexity you would expect that the noise would not change on the plateau, so it's constant. Also, this calculation that we do highly suggests that the noise that we have is non-Gaussian, because it's just not coming from weak contractions of pairs of boundaries, as in the case of the spectral form factor, and this is because of this kernel that pulls eigenvalues close together. And perhaps the most important caveat that I should mention is that you can ask whether we are calculating the variance right, because we also need to make further choices when we calculate the variance, because now we have 2 geodesics, so we don't only need to worry about self-intersections, but we need to worry about whether the 2 geodesics intersect. And again, the case when we can do the calculation using just Mirzikhani's recursion relation is the case when we restrict to non-intersecting geodesics. So you could ask whether that's something that could fix the problem. Okay, very good. So last thing I would like to say is about this formula that we get that is rather simple, and it just depends on the spectral 2-point function. So an important comment here is that I was talking about JT gravity so far, but you can just do this calculation with more general dilaton potentials using the methods in these references, and you find the same formula. And what this more general dilaton potential does, it's changing the matrix model. So it will be a different random matrix potential. Okay, so this formula makes sense in any matrix integral. So you can just go ahead and remove the random matrix average and write down an expression in a quantum system. So we call this spectral complexity, and I have already focused on the late time limit, where we don't really care about what kind of Cauchy's dress this factor here, just that we have this this 1 over the energy difference squared. Okay, so this is a very simple quantity. And now I will try to give you one interpretation for this quantity, which is the following. So you can think about this quantity as measuring the following. It tells you how much of the Hilbert space is spanned by time-evolved thermophile double states up to a given time. So you can think about this set of states for times smaller than t, and you can think about how much of the Hilbert space roughly this spans. So how does this work? It's very simple. So you can define the following density matrix. It's a kind of mixed state that you get by summing up sort of the projectors to different time-evolved states. So these are not orthogonal projectors, but this density matrix is still valid density matrix. So how do I want to use this to measure the question I was saying? So if imagine for a moment that this density matrix was a projector, so maximally mixed state that projects to a subspace of d dimensions, then it would have a form like this, and its secondary entropy would be the inverse of this dimension. So this is a very simple quantity, and I just want to think about this secondary as the inverse of an effective dimension of this Hilbert space. So in general, what you have is that the rank of a density matrix is lower bounded by this inverse of this secondary. Okay, we need this lower bounding anyways, because this is a discontinuous quantity that actually likes to jump off to infinity pretty quickly. And if you define various types of smoothed versions of it, then this inequality will still hold. Okay, so I call this effective dimension, and why it's a nice quantity, because of course for this state you can go ahead and compute it. This is just you get some formula in terms of the spectrum, and what you get depends on the partition function, and what appears there is this spectral complexity that comes out from gravity. It's not exactly the same thing, the two things, but one is a function of the other. And the interesting thing here is that if you have a function that kind of has linear growth and saturation at exponential entropy time, and you plug it into this function, you get a similar other function. So they kind of behave very similarly. They will have some different slope here and some different plateaus, but these will differ by order 1 numbers, like pi square over 3. Okay, so this is one interpretation that you can give to this quantity that is in the spirit of sort of what complexities is set out to measure to begin with. Okay, so let me summarize. So what I told you about is I told you about how to define a regularized non-perturbative volume in JT gravity. So I gave you a particular regularization, but then I also told you that the divergences are time independent. So you can just always think about the time derivative of this volume. That's a finite quantity. And then I showed that this quantity saturates at exponentially large time in the entropy. And this is expected also from complexity. Okay, so what you find result is very similar to the spectral form factor, but the origin of the ramp and the plateau are different. So they both come from universal cancellations in random matrix theory, but they are not the same cancellation. Okay, so there are lots of questions that we haven't answered and that are somewhat puzzling. So first of all, in order to get this cancellation and this volume plateau, I needed doubly non-perturbative effects. So I needed to complete JT gravity with the matrix model of Saad, Schenker, and Stanford. And this is so crucial, actually, that if you just truncate the genus expansion, any finite order in the genus expansion would give a very wrong approximation for the volume curve. So it's kind of crucial thing to have these doubly non-perturbative things. But we don't really understand the geometric origin of them. So it would be good to understand what's the geometric origin of the saturation directly in the gravitational theory. An obvious question is whether this quantity that I have shown you in the last few slides, spectral complexity, can match any kind of definition of actual complexity. Does it have a chance or not? Another puzzle that I was kind of telling you about is the late time variance. It's larger than expected and it's not equilibrating, but this comes with many assumptions. And lastly, you can ask what happens in higher dimensions. Is the spectral density 2-point function still in control? Since we're talking about times that probe the discreteness of the spectrum, it's reasonable that it's still kind of governed by random matrix theory. And also since JT gravity appears as a dimensional reduction of near horizon region of various black holes, you can ask whether these conclusions hold in those cases. Okay, that's all I wanted to say. Thanks a lot for your attention.
Thank you very much, Gabor. So are there any questions?
I had a quick question.
Yeah, go ahead.
Sorry, I didn't raise my hand, but
Go ahead.
Yeah. So this complexity story relies on this intuition of a quantum circuit, and whether or not we have a holographic picture of a theory seems to rely on other features like the large N limit, strong coupling, perhaps some properties of the spectrum. And in fact, spatial locality isn't a necessary component of what renders a theory holographic and whether or not it has a dual spacetime. Now, I don't understand what role these details that distinguish holographic theories versus non-holographic theories play in the discussion of complexity so far. Is there some thoughts you can share on this?
Yeah, so let's start with large N. So large N is needed for this quantity to grow for parametrically long time. So since the entropy scales like N squared, this plateau.
Large K is not enough for that.
Sorry?
Large K is not enough for it to grow for a long time. You also need large N.
What is K? Sorry. Like
it's what you told me it was.
Yeah. So no. Yeah. Large N is one way to get large K. So K is like maybe you can also think about it as like local Hilbert space dimension, or like how many states you have available at a given energy. Maybe that's.
I see. So for you, K and N are the same. I thought K was more like the sort of spatial degrees of freedom in your lattice theory, not the number of degrees of freedom per spatial point, which is what I would have called N.
Yes. Yeah. I think I agree. So yeah, you can likely make without large N this growing period long and a plateau large by just considering a large system that is like, because these things scale with the volume and they will appear in this time scale and this value. So that's a good point, but like one way of getting it is having large N, but it's not an exclusive way. So let me comment on strong coupling. So strong coupling is believed to be needed for this growth to last as long as it can. So if you have a weakly coupled system, there like you would expect complexity to not go very large and to kind of start to oscillate because you find shortcuts very soon, because like the intuition is that time evolution doesn't explore a lot of Hilbert space. There's infinitely many conserved quantities, so it stays in some small corner of it, and yeah, sorry. Yeah, so it stays in some small corner of Hilbert space, so it will just cap off at some smaller value at some smaller time. If you have some ensemble in a given system, it would just like doing some oscillations. On the other hand, in a chaotic system, you would expect there is no shortcut and the growth is there for a long time, and the plateau is very large in complexity. On the other hand, I agree with you that you would perhaps expect this behavior in just some generic chaotic system that doesn't have infinitely large coupling. So it's not really something that at least these kind of features of complexity are not expected to be able to tell apart large stringy corrections versus small stringy corrections, as long as it's not tangentless. But these comments apply for these spectral.
Yeah, at some point, it would be nice to see something that really distinguishes the system, a generic strongly interacting chaotic system that truly has a piece of local spacetime inside of it from some hot cup of coffee. You know what I mean? At some point, I'd like to know whether I'm studying gravity or random generic
things
chaos.
that you can use to do that, right? So, for example, the OTOC is such a thing.
Yeah, right. So, but I'm asking specifically in the context of this complexity story. Yeah. Anyhow, okay. Just wanted to hear the thoughts.
Gideon.
Hi, yeah, just a stupid technical clarification. All the way at the start of the talk, you mentioned that your action has this function f in it, which parameterizes some like wiggle, some distortion of the boundary of the disk. Can I identify this mapping f with like the quasi-symmetric maps that people use to parameterize Teichmüller space of the disk?
Yeah, sorry, I just wanted to go there.
Yeah, perfect.
So can you define to me quasi-symmetric map?
Yeah, so it's the boundary, it's the restriction to S1 of the solutions to the Beltrami equation. So when I just parameterize Teichmüller space with some Beltrami differential mu, then it gives me some Beltrami equation. And if I restrict the solution to this equation to the edge, to S1, it's a useful way to parameterize the Teichmüller space of the disk. So I was curious, since it seems very similar, I was wondering if it is actually exactly the same thing.
Yeah, I can't tell. Sorry.
That's right. Thanks.
Actually, can I also go for a technical thing then? If you have
Yeah, go
that
ahead.
curve of the complexity, like there was on one of the, it happened several twice. But what was this downward peak there towards the end?
Sorry, yeah, should I go to?
Yeah, I don't know. It happened like towards the middle and towards the end.
Towards the end.
No, it should come here as well. Like just a curve that you had where you had the ramp and the plateau of the complexity.
Okay. Yeah.
Oh no, here it
please.
was. It was like what just below.
Sorry, this
Yeah,
figure?
I think. Yeah. Just
Yeah.
what happens over there? Like why is there this downward peak?
What happens where? Sorry.
What happens there after e to the power of 4k? Like why does it go like
At this
down
one?
there? No,
Yeah, so,
just like why does it go down after the plateau there? Like why does it like where is the
why does it go
downward peak?
down?
Yeah, what is it there?
Yeah, so this is a Poincare recurrence. So I should probably not put it on the figure because I haven't talked about it. But yeah, so what happens is that if you wait truly long enough, not just exponential in entropy, but double exponential in entropy, then so by this time, what happens is that time evolution has explored all possible states. But if you are waiting long enough, then it will just eventually get back close to the original state again.
Oh, okay.
So you expect it to kind of dip down because again, it just by chance finds it and goes close. Goes close. Yeah.
And then it will just go up again and to the
So it's
height.
sort of. Sorry.
And then it will just like go up to the height of the Cmax, right? Or...
Yeah. It comes back again and then small fluctuations here again, and then every
it will go down and up.
Yeah, there's like some dipping in. It doesn't go all the way down because it doesn't hit exactly the original state, but it has like a large downwards fluctuation like this over an extended period of time.
Okay, thank you very much.
Sure.
If there are no more questions, we can thank Gabor again and close the session. I would like to invite everyone to just enter Gather Town for a few minutes of socializing if you want, if you have time.